Welcome, everyone. Imagine an electric vehicle as a character standing at the start of an invisible racetrack. This racetrack is called the driving cycle. It is not a physical road, but a speed versus time pattern that tells the car when to speed up, slow down, stop, and move again. The EV has a clear mission. First, it must predict how much energy it will use. The energy required depends on the forces acting on the vehicle, and the EV must overcome all these forces to move forward. Second, the EV must master propulsion. This determines how much power the motor must deliver at every moment of the driving cycle. Third, the EV must harvest energy while braking. When slowing down, energy can be recovered, and regenerative power equals regenerative efficiency multiplied by braking force multiplied by velocity. As we begin, imagine feeling every force, every acceleration, every air resistance, and every moment of regeneration. The invisible racetrack is ahead. The mission has begun. Let us start driving the car mathematically before we drive it physically. Imagine a map called the torque-speed plane. On one side is speed, and on the other side is torque. As the EV moves through the driving cycle, it travels across this map. There are four main territories. First is the constant torque lowlands, where at low speeds torque stays constant while speed increases. Power equals torque multiplied by speed, so when torque is constant and speed increases, power increases. Second is the constant power highlands. At higher speeds, power stays constant. Since power equals torque multiplied by speed, if power is constant and speed increases, torque must decrease. Torque equals power divided by speed. Third is the positive torque motoring realm, where torque is positive, the motor pushes the vehicle forward, power is positive, and energy flows from the battery to the wheels. Fourth is the negative torque generating realm, where torque is negative, the motor slows the vehicle down, power is negative, and energy flows from the wheels back to the battery. As the EV follows the driving cycle, it moves through all four territories. Each transition is like a passport stamp, and the torque speed plane becomes a journey map marked every second of driving. There are different driving cycles like different chapters in the same story. The Urban Dynamometer Driving Schedule, UDs, represents city driving. It includes frequent stops, low speeds, and many accelerations. The Highway Fuel Economy Test, HWFET, represents highway driving. It has smoother acceleration and higher constant speeds. The Worldwide Harmonized Light Vehicles Test Procedure, WLTP, is a global testing cycle. It combines urban, suburban, and highway conditions in one longer and more realistic pattern. The Indian Driving Cycle, IDC, represents typical driving conditions in India, with its own unique speed variations. From the EV's point of view, the driving cycle is not just a graph. Every driving cycle contains phases of acceleration, phases of constant speed cruising, phases of deceleration, and idle periods, where EVs do not consume traction energy. It is a performance script written by the world, and the EV must follow every second of it perfectly. On the invisible racetrack, the EV is not alone. Four powerful villains stand in its way, and each one tries to block its motion. The first villain is aerodynamic drag. It pushes against the vehicle as it moves through the air. The second villain is rolling resistance. It comes from the contact between the tires and the road. The third villain is grade defiance. This is gravity acting on the vehicle when it climbs a slope. The fourth villain is inertia. It resists any change in motion, especially during acceleration. Together, these four villains combine into one total force. Total force equals mass times acceleration plus rolling resistance plus aerodynamic drag plus grade force. Every second on the road is a battle. From the EV's point of view, this is not just physics. It is a constant fight against drag, resistance, gravity, and inertia. And the mission is clear. Overcome them all and keep moving forward. Now let us trace the force step by step. It begins at the road. The tire pushes against the ground with a traction force, and this force creates torque at the wheel. Wheel torque equals traction force multiplied by wheel radius. This torque then travels through the gear system. Motor torque equals wheel torque divided by gear ratio and drivetrain efficiency. The gear system provides mechanical leverage, allowing the motor to produce the required wheel torque more efficiently. From the EV's point of view, the wheels are like hands pushing against the road, and the motor is the muscle inside. Through gears and efficiency, The EV uses mechanical leverage to move forward with strength, precision, and control. The driving cycle can be seen as a speed vector. This means speed is recorded at small time steps. In simple form, we write V equals V1, V2, V3, and so on. Each time step has a small change in time called delta t. Acceleration is calculated as change in speed divided by change in time. Every small delta t becomes a cliffhanger. Will the vehicle speed up, slow down, or remain constant? From acceleration, we calculate force. From force, we calculate torque. From torque, we calculate power. And this loop repeats every second. Speed leads to acceleration. Acceleration leads to force. Force leads to torque. Torque leads to power. Step by step, second by second, the EV follows this mathematical adventure through the entire driving cycle. We connect force, power, and energy. First, traction power is calculated from force and speed. Next, battery power must include drivetrain efficiency. Battery power equals traction power divided by drive efficiency. When the vehicle is braking, power becomes negative. During these negative segments, regenerative efficiency is included. Recovered power equals regenerative efficiency multiplied by braking power. To find total battery energy, we integrate battery power over time. This process is like bookkeeping. Speed leads to force. Force leads to power. Power over time becomes energy. Step by step, the speed trace is converted into watt-hours, revealing how much energy the EV truly uses. Now we follow the designer's routine. Step 1, pick the driving cycle. Step 2, compute acceleration at each time step. Step 3, find the total force at each step. Step 4, calculate power at each step. Step 5, integrate power over time to find total energy. Step 6, size the motor and the battery. Peak power determines the motor and inverter rating. Total energy determines the battery capacity. Peak power defines how strong the system must be, while total energy defines how long the system can operate. The motor must be sized for the highest power demand in the entire driving cycle. Peak motor power equals the maximum traction power. This means we examine all time steps and select the largest value of traction power. Even a short 5-second hill climb can create the highest power demand. That brief burst determines the inverter power rating in kilowatts. The inverter must survive the worst-case moment, even if it happens only once. In contrast, average power is calculated as total energy divided by total time. Average power governs thermal design and driving range. So remember, peak power sets the inverter size, while average power affects heating and range. Let us analyze an urban acceleration phase. The vehicle mass is 1,100 kilograms, and the acceleration is 0.5 meters per second squared. The inertial force equals mass times acceleration, which gives 550 newtons. Now we add rolling resistance, which is 161.8 newtons. Next, we include aerodynamic drag at a mean speed of 5 meters per second. The drag force is 10.6 newtons. The total force becomes 722 newtons. Now we calculate power at a speed of 10 meters per second. Power equals total force multiplied by speed, giving 7.2 per kilowatts. Energy for this 20-second phase equals power multiplied by time. This results in 144.4 kilojoules. This completes phase 1, and now we open the 60-second urban energy ledger. Now we record the next entries in the urban energy ledger. Phase 2 is cruise. Acceleration is 0, so A equals 0. The total force is 204 newtons. Power equals 2.04 kilowatts. And energy for this phase equals 40.8 kilojoules. Phase 3 is braking. In this simple case, there is no regenerative braking, so the recovered energy equals 0. Now we add all phases. The total energy equals 185.2 kilojoules. To convert to watt-hours, we remember that 1 watt-hour equals 3,600 joules. So energy in watt-hours equals 185.2 kilojoules divided by 3.6. The total energy becomes 51.44 watt-hours. This completes the simplest numeric quest. The units are consistent: force in newtons, power in kilowatts, and energy in kilojoules and watt-hours. The ledger is balanced and validated. When the vehicle slows down, energy is not always lost. During deceleration, regenerative braking can recover energy. The recovered energy during a small time step is calculated as E. Regen equals regenerative efficiency multiplied by mass multiplied by the absolute value of acceleration. multiplied by velocity, multiplied by delta t. This recovered energy becomes a credit. During positive acceleration segments, the battery supplies energy. During deceleration segments, the battery receives energy back. Net battery energy equals total positive energy minus total regenerated energy. In equation form, energy net equals energy consumed minus energy regen. This is like keeping a ledger. Energy used is recorded as a debit, and energy recovered is recorded as a credit. At the end of the driving cycle, the final balance gives the true battery demand. Now we are ready to apply this to a full cycle integration exercise. Now let us analyze a drive cycle with an uphill of 5 degrees. First, calculate the grade force. Grade force equals mass multiplied by gravity multiplied by sine theta, giving Fg equals 1025 newtons. Rolling resistance force equals 176.6 newtons. And aerodynamic drag equals 52.9 newtons. Total force equals grade force plus rolling resistance plus drag. So F total equals 1,254.5 newtons. Power equals total force multiplied by speed, giving 13.9 kilowatts. Energy equals power multiplied by time, which gives 417 kilojoules. Converting to watt hours, energy equals 116 watt hours. This shows that adding a 5-degree slope nearly doubles the energy compared to flat cruising. The hill changes everything. Let us compare the two cases at the same speed. Flat cruise energy is 41 watt hours, while uphill energy is 116 watt hours. The slope nearly triples the energy demand. Why? Because of potential energy. Potential energy equals mass multiplied by gravity multiplied by change in height. In equation form, E potential equals m times g times delta h. When the vehicle climbs, this energy is stored as height. Without regenerative braking on the way down, this energy is irreversible and cannot be recovered. In hilly driving cycles, this potential energy term often becomes the largest part of total energy demand. The road angle can dominate the energy budget. Let us compare peak power and average power. During uphill driving, peak power reached 13.9 kilowatts. During steady cruise, average power was about 2 kilowatts. These numbers are very different. The inverter must be designed to handle the maximum power. Even if 13.9 kilowatts occurs only briefly, the inverter must safely deliver that value. Battery capacity in ampere hours is mostly determined by average power and total energy. Average power affects range and battery size. Peak power affects inverter rating, semiconductor current limits, thermal design, and overall system cost. In simple words, average power defines how long the vehicle can run, while peak power defines how strong the power electronics must be. This is a student assignment for you to work out on your own. Now we begin explaining a complex multi-segment quest. Segment 1 is acceleration from 0 to 50 kilometers per hour in 10 seconds. Segment 2 is cruising for 40 seconds at constant speed. Segment 3 is climbing a 7-degree slope for 150 meters at 40 kilometers per hour. Segment 4 is decelerating to 20 kilometers per hour with 60% regenerative braking, where regenerative energy equals 0.6% multiplied by braking power multiplied by time. Segment 5 is traveling 500 meters on flat road at 20 kilometers per hour. For the entire trip, compute acceleration using A equals delta V divided by delta T. Compute total force using F total equals MA plus F rolling plus F drag plus F grade. Then compute power using P equals F total times V. Include regenerative credit during braking. And finally calculate net energy in watt hours by integrating power over the full journey. This is your complete full cycle energy mission. Energy determines range. First, calculate energy per distance. Energy per kilometer equals net watt hours divided by total distance. In equation form, watt hours per kilometer equals WH divided by Kn. This value gives the true energy consumption of the vehicle. Next, multiply this number by the daily driving distance. Battery energy required equals watt hours per kilometer multiplied by daily kilometers. In equation form, battery WH equals WHU per km times daily Kn. This tells us how large the battery pack must be. It is not peak power that determines range. Peak power sets the motor size, Energy per kilometer determines whether a 24 kilowatt-hour pack or a 40 kilowatt-hour pack is required. Range is an energy question, not a power question. Now it is your turn. Create your own local driving cycle. It could be a campus shuttle, a delivery van, or a three-wheeler. Record real GPS speed data over time. This gives you a speed vector, where v equals f of t. Filter the data to remove noise, then calculate acceleration. Acceleration equals delta v divided by delta t. For acceleration, compute total force. From total force, compute power. Then integrate power over time to find energy in watt-hours. Finally, propose the motor peak power in kilowatts and the battery capacity in kilowatt-hours. Design your EV based on your own real-world duty cycle. 4 forces act on the vehicle: acceleration force, rolling resistance, aerodynamic drag, and grade force. Total force equals the sum of all these forces. F total equals ma plus F rolling plus F drag plus F grade. Power is calculated from force and speed. P equals F total times V. Energy in watt-hours comes from integrating power over time. E equals integral of P with respect to time. Peak power determines the motor and inverter rating in kilowatts. Total energy determines battery capacity in kilowatt-hours. Regenerative braking subtracts energy credit from the total demand. In the end, every EV design begins and ends with this energy ledger. This script defines the electric vehicle as a complete system. Designing an EV without a driving cycle is risky. If we ignore the drive cycle, the vehicle may become overbuilt, with a battery that is too large and too heavy, or the motor may be too small, causing weak acceleration and power stalls. Without this, design becomes guesswork. The driving cycle is the heartbeat of EV design. It defines motor peak power, it defines battery energy in kilowatt hours, it shapes controller logic, and it supports accurate range predictions. This script is not optional. It is the non-negotiable blueprint that anchors performance, efficiency, and reliability. Thank you all. See you in another session on electric vehicles. Until then, goodbye.